In this session, I shall prove two formulae about differentiation. The first one, for y is equal to x squared, I shall prove that dy by dx is equal to 2x. The next one, if y is equal to 1 over x, I shall prove that dy dx is equal to minus 1 over x squared. Let's start. The first one, when y is equal to x squared, I shall start with the definition of dy dx. There are a few ways to think about it. The easiest is to start from a picture of a graph. If I think of a graph of this y equal to x squared, looks a bit like this, a curve. We can think of dy dx as the gradient of a line touching the curve. So if I think of a point there, let's say that point is just it has the x coordinate equal to just x. If I think of a line just touching this point, I'll try to draw a straight line. So that's a straight line that touches this point. The gradient of this straight line, which we would call the tangent. Right? Tangent is the name of a straight line that touches a curve. The gradient we can find in the usual way for a gradient. We can imagine drawing a right-angled triangle like this, with the tangent as the longer side and the other two sides vertical and horizontal. Then the gradient is just the vertical side divided by the horizontal side. Let's say I call that A and B. So gradient of this tangent is just A over B. So that's how we would understand the gradient. But the idea here is that given this formula, can we find another formula for this gradient, so that if I know x, I can just use that formula and calculate the gradients without having to draw this line and the graph and actually measuring out A and B and then calculating the tangents, which is quite a lot of work. And that's what we want to do. We want to prove that this is the formula, that this formula 2x can be used, to calculate the correct gradient to get the same answer as if I do this on the graph. And the mathematical idea goes something like that. We start by thinking of another point some distance away. Now, if I think of that point as to have a x value of just x, then that other point, let's say it is separated from x by a small distance. Let's say h. Okay, so that point there would be x plus h. We would have x plus h as its x coordinate. Okay. So we can think of, let's think of a line joining those 2 points. Okay, suppose I have a line, straight line joining those 2 points. Then if you think of the gradient of this line, you can see that this line is steeper than the tangent. So this line would have a bigger gradient. Now, if I imagine, if I call this point A and B, if I imagine moving the point B towards A, then you can see that the slope of this line gets closer and closer to the slope of this tangent. And eventually, if B gets extremely close to A, then the gradient of this line would get extremely close to the gradient of the tangent. So it is this idea that we can use to find a formula. And the plan is to first start by writing down an expression for the gradients of AB using this equation, and then think about what happens to that expression when this distance h goes to 0 or becomes extremely small. So let me start by writing down the gradients of AB. Gradients of the line AB. I can think of, again, a triangle, a right-angled triangle with AB as the longest side. Then the horizontal side is just h. Alright, I need to take vertical over horizontal. Horizontal is just h. And the vertical side I can find by subtracting the y values of B and A. Since the x value of A is just x, the y value of A is given by this formula. It is x squared. The y value of B, I can use the same formula, but this time x is x plus h. So the y value of B is x plus h squared. So therefore, if I subtract those two, I would get the vertical side of a right-angled triangle to find the gradient of AB. So therefore, the vertical side is just that minus that. X plus h squared minus x squared. Okay. And as I described just now, we need to think about what happens to this gradient, this expression, when this distance h becomes extremely small. Now if I just look at the expression directly, we can see that when h becomes extremely close to 0, I can write it this way with an arrow pointing to 0, and I would understand this to mean that h will get extremely close to 0, then this gradient would become. Now if I look at those two, when h is actually 0, I have x squared minus x squared, which is 0. And when h goes to 0, I have 0 at the bottom as well. So that doesn't help, right? 0 over 0. That's not good. So we need another way to do it. And actually, there is another way. Let me start by simplifying this. I'll write it down here again. So gradient of AB, right? I'll call that equation 1. So this follows from equation 1. I am going to expand this. That gives x squared plus 2xh plus h squared coming from there. And I have minus x squared over the h here. And I can simplify this because I have x squared here and I have minus x squared here, so those two cancel. And here you see that I have an h in this term and I have h squared in this term and I have h at the bottom. So I can separate this out into two fractions, divide each term by h. So this term divided by h and h cancels, gives 2x. H squared over h gives h. Now let's think about what happens when h becomes very small. When h tends to 0, as we can describe this, that's how we would read this. When h tends to 0, this gradient, if you think about what happens when h tends to 0, h itself just becomes 0. And that's 2x. Now that is much better. And as you can see, we have actually obtained and proved this formula that we wanted to prove. So this completes the proof, really. Okay. And while we are here, let me just mention some notations, symbols that are often used for this kind of calculation. Now the h here, I've thought about the h here as a small distance between between the x value of one point and the x value of the other points. Now another way to think of h is to think about it as a change, a small change in x. So x changes to x plus h. Therefore h is a small change. H, so small change in x. So the proof is done, more or less. I'm just clarifying some of the meanings of the terms. A small change in h h is a small change in x. Right. Now there is another way to write a small change in x. We can make use of this expression, delta x. That funny symbol there is the Greek letter called delta. And in mathematics, delta is often used to represent the idea of a small change. Not small change as in a little bit of money or coins, but small changes as in the difference when x changes by a little bit. Okay, so we think of this symbol delta as an idea, right? As an idea, rather than a number, as we would think of x in algebra, right? We think of x as a number, but when we see delta put next to the x in mathematics, the usual way is to think of the delta as to have a meaning like this. So if you see delta x, it just means small change. It doesn't mean a number delta times another number x. And we represent this delta x as a single symbol for a number. And this corresponds to the h that I've been talking about. Now, in the same way, we can think of a change in y. So when x changes by this amount, a goes to b, and therefore y changes by that amount. And this change in the y can be represented by the same symbol delta. So I would write delta next to the y, and this means a change in y. Okay. So therefore, the gradients, if I think of the gradients again, here, the gradients of AB, I've written it down as the vertical distance from A to B divided by the horizontal distance from A to B. But now I know that I can think of this vertical distance as the change in y, horizontal distance h as the change in x. So therefore, I can write the gradient as the change in y divided by the change in x. Okay. So this idea that h tends to 0, I can also write it as, alright, think of it as the same as writing delta x tends to 0. Okay. Now, if you look back at this calculation, where I try to calculate what happens when h tends to 0, I find that we can actually, because we might use this idea quite often when we do calculus, there is a symbol to represent this whole idea of finding the answer when for the gradients when h tends to 0. Okay, the sun is disappearing behind the clouds, so we need some lights here. Right, so to represent this idea, there is a symbol that is often used. Okay, we could use this symbol L, I, m. And then I would put delta x tends to 0, put this symbol delta x arrow 0 at the bottom. Okay. Oh, not yet. I would put delta y over delta x next to that. Delta y over delta x next to that. And this should give us the gradient. Okay, so that's the idea of this symbol. We should read this symbol to mean the limit as delta x tends to 0 of delta y over delta x. And we think of this as a limit because of the problem that we have seen with 0 over 0. If you remember, if you simply substitute h equal to 0 into this fraction, we end up with 0 over 0. So we have to be careful in doing that. What I've done is I've made these rearrangements and obtained an expression that doesn't give us 0 over 0. But the idea is that we can we have to really think of this calculation as finding an answer when both the top and bottom of the fraction gets very close to 0 but not exactly 0. If you think of it this way, then instead of 0 over 0, we can think of this as two extremely small numbers over each other. And when they get extremely small, this is the answer that we get, 2x. Okay, so as long as they are not really 0 over 0, the idea is that we can find a proper answer. So anyway, this is what this means. And there is a symbol that we often use to denote this idea, and that is dy dx, which becomes familiar when you do calculus. So that completes the proof for the first part, dx, and I've also explained how this dy dx symbol comes about. So we should think of dy dx as a symbol. Next, I shall go on to prove the next part. Okay, quite a bit of shadow here. We're still waiting for the sun to come out. Part 2. Right, we want to prove that we want to find dy dx when y is equal to 1 over x. So now we can use the same idea as before. We can think of drawing a graph for that. Right, but it might get a bit difficult to, if we have to draw the graph each time, to think about it. So rather than drawing the graph, we can think of another way of using the formula. Okay, this is how I would think of it. If I think of this as a function of x. Now if you remember, we want to find dy dx, and it is limit as delta x tends to 0 of delta y over delta x. I can also think of this as a limit. Now remember that I've used h for delta x just now. If I use h again instead of delta x, think of this formula where that I've used just now, where I have the change in the y value over h, the horizontal distance. Now the change in the y value, I can think of finding that by calculating its function. I can think of calculating the change of this function when x increases by h. So at first I have fx, then when x increases by h, I have f of x plus h. So this is the difference. So this is another way of writing this expression. And this way of writing the expression is in sometimes, right, like here for what I'm going to do, it's a more obvious expression that will tell me what to do next when I want to find the dy dx for 1 over x. So let me try this out. Dy by dx, limit as h tends to 0 of this. So fx is 1 over h, and if x becomes x plus h, I have 1 over x plus h minus fx, which is still 1 over x, minus 1 over x divided by h. So this is it. And once again, we cannot simply substitute 0 into the h there and there, because we would end up with 0 over 0. Right, so the way to do it, to avoid that problem, is to first try and simplify this, or rearrange it in some way to remove the possibility of getting 0 over 0 in the fraction. And the idea is that we would hope to find some way that would allow the h at the bottom to cancel out with something from the top. Now let me start by combining this fraction. I shall write the over h as just 1 over h. Okay, I'm going to put those two into a big bracket. I shall combine the denominators to form a single fraction. So x times x plus h, I just multiply together the two. Then on the top here, when I combine them, I'll multiply x and 1 to give x, and for that term there, I'll have 1 times this, which is x plus h, and there's a minus sign between. I insert a minus sign here, but I must be careful that x and h are supposed to be added together first before we do the minus. So I need brackets over that. Okay. Now, if I then simplify this, I get, when I remove the bracket, I find x minus x, which is 0. So I'm minus x minus h over x plus h. So x and x cancels, and the h there cancels. have minus 1 left at the top, and the bottom is still the same. Now I've simplified the expression, and if I now think of what happens when h tends to 0, if I just replace h by 0 here, I'll get minus 1 over x times x, which is fine. I don't have a 0 over 0 problem here. So therefore, this is the answer. And if we look back at what I wanted to prove, dy is equal to minus 1 over x squared, you see that we have completed the proof here. We'll stop here.